In the last class, only one problem was solved on from the chapter of hydrostatics. There, one rectangular plate was used for the calculation of force, where the plate was held vertically. Here also same case, but the orientation is somewhat different. Okay, say again we are using water as the liquid. So here this is the free surface of water. Okay, free surface of water, and here the plate is held vertically, but orientation is like this. Okay, rectangular plate again, and suppose this is denoted by A, B, C, D. D, this is at a depth of 1.5 meter from the free surface of water. Okay, and this length is 2 meter and this length is 5 meter. Okay, so here we have to calculate force exerted by static water on one side of the plate only. Okay, so to solve this problem, here also again you have to take that elemental strip which is parallel to the free surface of water, but there will be some problem in integration. So what we will do, say we are taking here this elemental strip, this is parallel to the free surface of water. Okay, suppose here the width of the element, this length of the element, it is B, and it is at a depth of y from the free surface of water, and this width is dy. Okay, and suppose this length is B, then B into dy is the elemental area. So elemental area, it is what? It is B into dy. Okay, then what is the force on that elemental area? Force is denoted by dF, which will be equal to pressure on that elemental area P multiplied by B dy. Therefore total force F, it is equal to P means rho g h, here h is not there, y is there, so rho g y into B dy. Okay, here density of the fluid is constant and g is also a constant, so these two terms can be taken outside the integral sign, so it becomes rho g by dy. And you can clearly see that b is a variable here, b is not constant. In the previous case b was constant, the length was constant, but here it is changing. Here at the top it is 0, gradually it is increasing. Then if you draw one horizontal line from A and another horizontal line from C, so you will get three parts. Okay, say this is part number 1, the first one, part number 1, this is part number 2, and this triangle is part number 3. So you have to separately calculate the forces on all these, on this triangle, this parallelogram and this triangle, and then you sum up. So you will get the total force. Okay, so B is a variable, therefore we can write rho g integration of Fy into y dy. Here B is written as a function of y. Okay, then for three parts you have to integrate this way. For triangle number 1, I am writing just here 1 to denote triangle number 1. Okay, Fy y into dy, plus for parallelogram it is denoted by 2, so Fy into y into dy, plus triangle number 3, so it is again Fy y dy. Okay, now for each case we have to find out that y, Fy. Okay, so here still the orientation of the rectangle is not specified. Suppose if you extend the line AD, okay, it makes an angle with the free surface of water. Say the angle is 30 degree. Just for example, we are taking 30 degree, okay. So 30 degree. So now we are considering the triangle number 1, okay. First you draw one perpendicular on this line from D, okay. Since this angle is 30 degree, so this angle must be also 30 degree, right? This angle must be 30 degree. Therefore, suppose this height is h, okay, this height is h. So h can be calculated easily from here. H is equal to how much? H by 2. This is equal to sine 30 degree. Therefore h is equal to 2 sine 30 degree, okay. So now h is known. Now we have to write this width b in terms of y. That is our m here, okay. This width as a function of y. So this elemental strip, this is parallel to this line. Therefore this small triangle and the large triangle, they are similar triangles. Therefore this height divided by the total height is equal to this length divided by this length, okay. What is this length? Still it is unknown. So this length h is now known. From here to here, suppose it is x1, and from here to here it is x2. This angle is 90 degree, this is 30, that means this should be 60 degree. So x1 is how much? X1 by 2 is cos 30. So x1, this is equal to 2 cos 30 degree, okay. And x2 can be written in terms of this h, okay. x2 by h is equal to cot 60 degree. So x2 equal to h cot 60 degree, right? Now the base length is known, it is x1 plus x2, okay. If you add these two things, you will get the base x1 plus x2. Now suppose this length, it is say y1, okay. Then using the properties of similar triangles, we can easily write y1 divided by h equal to this base length b, means here x1 plus x2, divided by, sorry, it should be just the reciprocal, okay. I have made a mistake. X1 plus x2, and this is how much? This is b, okay. So here b is equal to how much? B is equal to then x1 plus x2 into y1 divided by h. Now everything is known in the right hand side. x1 is known, x2 is known, y1 is also known. y1 is equal to how much? y1 is equal to y minus 1.5, okay. y1 is equal to y minus 1.5, this much of meter, okay. So now b is known in terms of y, okay. Since b is known in terms of y, then you can do the first integration, this one. Here limit will be how much? Limit will be, y will start from 1.5 up to this. So for the first integration, this one, I am writing this one, integration fy y dy, okay. This is equal to, y will start from where? 1.5. Y will start from 1.5 and it will go up to 1.5 plus this h, okay, this h. And fy is what? Fy is this one, x1 plus x2 into y1 by h. I multiplied by this y into dy. So this way the first integration you can evaluate. For the second one, the length does not change, okay. The length does not change, but you have to know this coordinate, okay. The integration will start from here to here for figure number 2. And similarly, you can do the same thing for figure number 3. This way the total force can be evaluated, okay.